This is a talk that I gave to the Richmond Astronomical Society on December 14th, 2022 about robotic telescopes. This talk will cover how robotic telescopes came to be, who they're for, what they're good for, and what they're not so good for. And I will be discussing these images I took that you can see on this page with the telescope you also see. Now, as for where robotic telescopes came from, the top of the page here shows 3 different visual scopes from the product page of the Celestron website. You see a refractor, a C8 Schmidt Cassegrain, and a 10-inch Dobsonian. And on the bottom right is a typical imaging setup. You can see the equatorial mount, and it's fairly complicated with all of its parts you have to put together. And a fairly new field of amateur astronomy is electrical assisted astronomy, or EAA, and you can see an example of that in the lower left. The way this field of amateur astronomy evolved is from people who initially had visual scopes like this C8 you see up in the top center, and they adapted it for imaging, but it's still using an Alt-Az mount, so you're limited to taking short exposures. But their setup here is they have this laptop running software that can take all the short exposures, stack them together, do some processing, and show a near real-time image right on the screen. So people have been doing this for a number of years, and a couple companies got the idea of what if we built a system scope very similar to the one on the bottom left here that could put everything together for you and make the whole process very easy. So that's what robotic telescopes are. They're a all-in-one scope, camera mount, software, mobile app control, go-to plate solving. Some have autofocus, auto stacking, and some basic image processing. So they kind of do all those steps for you. And these are the examples of robotic scopes that are out right now. The upper right is by Unistellar, the EvScope, and the EvScope 2 at Equinox. All of those have about the same form factor. It has a 4.5-inch paraboloid mirror, and up here where the diagonal would have gone, they have a sensor that collects the light. And this eyepiece here is not an optical eyepiece, it's an electronic eyepiece similar to what might be on a mirrorless digital camera. So just a electronic viewfinder, so to speak, but it lets you see the image, although you could also see it on your mobile app screen. The Vaonis has 2 products you see on the bottom left. The bigger one here is the Stellina. It's an 80 millimeter f5 refractor, and the one in the bottom middle is the Vespera, which is a 50 millimeter f4 refractor. And the one on the bottom right is a new one that's just coming out from a company called Dwarf Lab, and it's a much smaller. It is a 23 millimeter aperture, 100 millimeter focal length refractor with a periscope design. It also has a wide angle lens that you can use as well. And this bottom one is significantly less expensive than the others, and it can also be used in the daytime. Now, comparing these robotic scopes to a traditional imaging setup, of course, the traditional imaging setup, you buy all the parts separately and put them together yourself. So they're modular in nature, which makes them more versatile. And depending on what parts you get, you could actually have a better system, but it could also be quite a bit more expensive if you buy all the best parts, and it's more complicated and usually heavier, and there's a lot of setup and configuration needed. One way to simplify a modular do-it-yourself system is to stick in within one ecosystem of products. For example, ZWO offers a lot of different products that all kind of work together easily. You can get their tripod, their mount, their ASI Air, which is a controlling mini computer. You get their electronic autofocuser, their own guide scope, and they have a whole collection of cameras that can be used for the main telescope or the guide scope. Of course, this you would have to add your own optical telescope. But this is one example of a modular system that is maybe a little bit easier to put together than trying to figure everything by yourself. The general pros and cons: traditional telescopes are more versatile and you can reuse existing equipment. The quality can be better depending on what you get, and you might be able to put together a traditional scope meeting the same specs as a robotic scope for a little bit less. And the robotic scopes come in to they have much greater simplicity and ease of use, and because they are a system design scope, the size and weight can be less because no one part is over-engineered more than it needs to be. And who are robotic scopes for? One big market is people first starting out in imaging and are intimidated about the complexity of imaging. Because you could use this, people get it and use it the first night they have it. They're out and using it successfully. And they can also are popular for people regardless of experience level if you just want an easy to use traveling rig. For example, I can throw mine in my car almost as an afterthought on a trip. Don't have to do a lot of planning on packing and taking it. Who is it not for? People who already have lots of equipment with a strong desire to reuse as much of that equipment as possible. These robotic scopes are all-in-one system scopes, so you can't mix and match other equipment you may already have. And they're not for people who want to image very small things, for example, planets, very small planetary nebula, small galaxies. The aperture and the focal length is just not suited for those. And if you want to take imaging farther and produce the best possible images, there are certain limits to what these scopes can do. And the cost, even though it is possible to build your own version of one of these robotic scopes for a little bit less, if that's only true if you discount your own time and effort in making all of the decisions and the struggle to get it to work. So if you do add in your own time, these robotic scopes could be a good deal. Now, a few words about Alt-Az versus Equatorial. The bottom animated GIF image is showing the Cassiopeia constellation as seen through an Alt-Az mount over a period of 5 hours. You see it's vertical here, and then over the course of 5 hours, it slowly rotates until it becomes horizontal. So there's a 90-degree shift here. And in the old days of film astrophotography, your only choice was to use an equatorial mount because the field of view with the equatorial mount rotates along with the sky because the axis of rotation is polar aligned with the axis of the Earth. And with an Alt-Az mount, the axis of rotations is horizontal to the ground and vertical. So this little square remains at the same orientation, you'd know the sky is rotating. So you cannot take a single long exposure with an alt-az mount unless you compensate with some kind of sensor rotation. But the way they do it in these robotic scopes and the EAA setups that use alt-az mounts is you take a bunch of short exposures. So if you take short enough exposures, like around 10 seconds, then there's not enough field rotation in that 10 seconds to notice. And so you can build up the total exposure. So if you wanted to expose for 5 hours with an alt-az mount, you would need 1,800 exposures. And let's say the Equatorial mount, the tracking was good enough where you could take 5-minute exposures. With 5-minute exposures, you would only need 60 exposures to get the 5 hours. So here you have 60 exposures, and on the alt-az you have 1,800 exposures. And so with both setups, you can go for the same imaging total integration time, but you just need a lot more with alt-az. And in the early digital cameras, they had a problem with read noise, where there's a little bit of noise injected with every exposure you took. And so that greatly favored having fewer, longer exposures versus many short exposures. But the newer digital cameras have very low read noise, so that penalty is not as great. There is something with the sensor threshold of detection that still favors the Equatorial mount. Imagine if you need a certain number of photons hitting a pixel before the pixel can register that something was there, like go between two different values, like maybe 0 and 1. And it could be you, in 5 minutes of collecting photons, you have enough photons hitting the pixel to detect it. But with 10 seconds, maybe you don't. And so it's possible with the longer sub-exposures that you can do with the Equatorial mount to be able to detect some of the dimmer and more subtle differences. So this just summarizes what I've just talked about. Some of the key things I haven't mentioned yet is the alt-az mounts can be much lighter because you're not having to hold the telescope at an angle not easily worked out with gravity. In the alt-az, you don't need to polar align, but you do with Equatorial. And a couple of years ago, this telescope at the bottom right from Dwarf Lab wasn't out yet, but I had to I made a choice to actually get the Vespera, the one in the bottom middle. And I made that choice for a couple of reasons. One was I was intrigued with the fact that you can put sensors right on the front, and also I like the small weight that this thing had, the small size and weight, and also the price point was pretty good. I've also learned that the EvScope in the upper right can also take filters. If you reach into the front where the sensor is, you can reach your hand kind of behind there and screw on an 1.25" filter. So this one also takes filters. And the Stellina, I think it has a built-in light pollution filter, and you can put on a solar filter on the front. And the Dwarf Lab at the bottom, it also can take filters. They have some little snap-on filters that go in this little optical window here. And this is what the Vespera looks like when it's closed and open at a couple different angles. And the Vespera is 50 millimeters aperture, about the size of a finder scope, 200 millimeters focal length, scope type apochromatic quadruplet refractor, and this is this Sony filter, the 462. This sensor is fairly small, but with this short focal length, those two together give you a field of view of 1.6 degrees by 0.9 degrees. And the system also has a Mosaic mode where the telescope can automatically take pictures up to this area, and you can redefine this area to make it longer, skinnier, or more squarish. Mount is Alt-Az, limited to around 10-second exposures, although you can change that if you want. And mounts only, for the whole thing only weighs 11 pounds. Telescope mount, tripod, everything. Physical size is pretty small. The Vespera does come with a number of optional accessories you can get through their website, as a dual band filter, a general light pollution filter, a solar filter, a little bit better adjustable tripod. This thing in the middle is a sensor, a dew sensor that will activate an already built-in dew heater integrated into the telescope to allow you to image longer when otherwise you would get dew forming. It's a backpack, extra little bubble level, and this little easy lock plate where allows you to take the thing on and off the tripod a little bit easier. The general use cases for the Vespera one is the electronically assisted astronomy, where the scope will generate the result of the stacked image as a JPEG file and deliver that to your mobile device so you can watch it become better and better over time on your screen. Also, at the end of the observation, it will produce a single TIFF file so you can post-process. And I have done both of these top two. For all the images I have posted online, I usually always take the TIFF file and run it through an image processing program to bring out the nebulosity. It also has the capability of saving individual FITS files that you could run through your own third-party software for selection, registration, stacking, and processing, just like you would do with a conventional rig. The physical setup is really easy. It has a very lightweight tripod that you can screw these little legs onto the center part. Then you screw the center part onto the bottom of the Vespera, and that's all. I did buy this adjustable leveling device you see right in the middle. This is not through the company, but I got it through a third party that allows for a very quick and easily leveling. So I can literally have this whole thing pre-assembled in my house, pick it up with one hand very easily, take it outside, plop it down, and with this little quick leveling system, I can have it level in just 2 or 3 seconds, and then I'm done. And that's the extent of the physical setup. For transportation, there's either the backpack you can get through the company or find another similar type of backpack, or you can get a hard case. I got this one through Harbor Freight, one of their cases that have this pluckable foam that I just plucked out an area that fit the Vespera and some of these other parts. So I've used this case on the left multiple times when I have taken this in the car to go somewhere to image. You control the Vespera and also all these different scopes through some kind of mobile app. And the workflow is you take your scope out, you turn it on, and after about 10 seconds, the scope starts to produce a Wi-Fi signal. And this can happen in your front yard or way out in the wilderness, totally away from human civilization. So the scope produces its own Wi-Fi signal, independent of having internet or anything like that. And then you launch the app and you connect to the scope's Wi-Fi signal. And then you choose a predefined observing location that you needed to set up beforehand. in the app, and that tells the app your GPS coordinates, and then the app knows your local time. So for all this alt-az navigation, it has to know the location and also the time, and then it can figure everything else out through plate solving. And so then there's an initialization step for the Vespera, and this usually takes maybe 4 or 5 minutes. What it will do, the scope will open up and start to take some pictures of the sky, do some plate solving to figure out where it is, where the sky is. Then it will go through this autofocus step that will take a series of pictures and minutely adjust the focus until all the stars become pinpoints. Then it will say it's ready for you to select a target. Then you have a couple options here. You can either select something from the catalog that the software provides of objects, or if you want to look at something not in the catalog, then you have the option to enter in the right ascension and declination celestial coordinates, and then it will just go to that place in the sky and you can take an image of whatever's there. So if there's a supernova or a comet or some other strange occurrence that's new that you want to take a picture of, you will be able to do it. And once you have made those choices, you can either take an image with the native field of view of the system, or you can choose to go into Mosaic mode. With Mosaic mode, the software provides you a little rectangle that you can adjust and rotate to define the area of the sky that you want to take the image of. And then once you select that, the telescope will take pictures in and around that area up and so that it can totally fill that area with data. So you start observing, and you can image for as long as you want. It could be 20 minutes or it could be 9 or 10 hours, just depending on how long the night is, and as long as you don't have any obstructions. The only exceptions is any alt-az mount is not going to be able to track very good right at zenith. And so you have to sometimes be careful that the object is not going to go right through zenith. If it will, you might have to image before it hits zenith or after, and or maybe right at zenith, it might not collect data for that period of time. There's also a plan your night mode where earlier in the day you can say, let's say I want to image one target from 10 p.m. to midnight, maybe something else from midnight to 2, and something else from 2 to 4. You can predefine all of those targets and when you want to image them, and then place your scope out in the evening and activate it, and then go to bed. And while you're sleeping, it can be imaging all those different things. And after you image, you can get the TIFF files off and optionally the FITS files by taking your PC or Mac and forming an FTP to the telescope after you have connected to its Wi-Fi, and you can then just click and drag the images off. And once you get those images on your PC, for example, you can do with them what you want with any programs you want for any post-processing. I've chosen to use Affinity Photo for my post-processing. That's a program kind of similar to Photoshop. And I do things like working the levels, adjusting the gamma and the black cutoff, also called the stretch. I use curves to add contrast and bring out faint nebulosity. And I usually run it through this Topaz anti-noise package I also bought to help clean up the image and back in Affinity, I do some vibrance and saturation adjustments. So kind of keeping with the easy to use philosophy of this robotic telescopes, when I do my post-processing, I rarely spend more than about 15 minutes on a TIFF file just to, and I found that that's all it takes to make it significantly better than just what the JPEG output of the telescope gives you by default. This is an example of seeing what comes right out of the telescope, the JPEG output, right to the mobile device, where each time this image changed, it doubled the integration time. The very last image right there where it got brighter is the example of what I was able to do with the TIFF file in my post-processing. So this is straight from the Vespera, doubling integration time. This image was taken over about 2 hours. So this second to last one is 2 hours, and then this is the post-processing. And this is the end result of my post-processing of this image. This is another similar one where each time the image changes, it's doubling the integration time. This is what you would see on your screen of your connected mobile device. And then the very last image is my post-processed TIFF file. So, and this was also taken over maybe 2 hours seeing this. And very last one is the post-processed one right here. And this is the Horsehead Nebula and the Flame. This is my post-processed TIFF file. So the Vespera does very well with these very large targets. And this is the Rosette. This was not a Mosaic. So if I would have done the Mosaic, I would have got the whole Rosette in. This is the Eagle Nebula, named because right in the center of the nebula is a little shape that looks a little bit like an eagle. The Fireworks Galaxy, the Phantom Galaxy. So it does fairly well on these kind of medium-sized galaxies as well. The part of the Veil Nebula. This is part of a supernova explosion. The Helix Nebula, Dumbbell Nebula. The Dumbbell Nebula is a fun one. It's so bright you can actually image this quite well even from severely light polluted skies. Although this image was taken at a darker site. The Pleiades. And this one, even though it's not a great image, I wanted to demonstrate the manual mode that the Vespera has. This was taken at a Bortle 7 location. The moon was out. But I wanted to take a picture where the core wasn't blown out. So I went into manual mode in the Vespera, and instead of doing a 10-second exposure, I only chose 5-second exposures. And I set the gain level as being lower. And so this made each exposure, I thought the default settings overexposed it. And so this was, I underexposed it on purpose so that the core would not get blown out. And you could barely make out here the stars of the trapezium, which is 4 little stars that are very close together at the core of the Orion Nebula. And so you can barely make them out here. And most pictures I see of the Orion Nebula, the center area is all blown out and you cannot make out the trapezium. So you can play around with the manual mode and do some of these kinds of adjustments. And this is an example of the stock settings where the core is blown out, but because I blew the core out, I'm also able to bring out this other nebulosity better. So this is the Orion Nebula and the Running Man. You can see the Running Man little shape up here in this nebula above the Orion Nebula. This was also taken at a Portal 7 location with about 5 hours of integration time. This picture would have been better if I would have gone to a darker site and done 5 or more hours. This was also a single mosaic taken from the telescope where I defined a skinny rectangle, getting the Orion Nebula, the Running Man, and the Horsehead and the Flame Nebula all in the same picture. So this was the telescope stitching all this together itself after I defined the rectangle. I did post-process this image in Affinity to bring out the nebulosity and the colors. Trifid Nebula, a globular cluster. Now, things that these robotic telescopes are not good for, they're not good for planets and very small things due to mainly the aperture and focal length limitations. Although I can say here that I have taken a picture of Neptune, just that little dot right in the middle. Now the moon, you get these kind of full disk pictures of the moon, but if you zoom in, the craters are, you can't really zoom in that well. It's just a digital zoom. So if you want to take close-up pictures of planets, Jupiter, Saturn, or craters on the moon, these really aren't the scopes for that. I don't have any picture to show here of Jupiter and Saturn, but they're not very impressive. So if you can't view one of these as the only scope that you would ever want to get, you would at least need this and some other maybe conventional telescope for planets and close-ups of the moon. This is another example of kind of the limitations of the Vespera. This is Stephan's quintet. Right in the center of the picture are these little fuzzy blobs, which are the galaxies. And this is the famous Webb telescope picture of Stephan's quintet. As a comparison, and this is another picture of Stephan's quintet I pulled off the internet from somebody's conventional imaging rig, which was probably an equatorial mount, probably a much larger telescope with much longer focal length, and they probably did pretty good job in post-processing, but you can see that the galaxies here show up much better. So if your goal is to get these really small things, then the conventional setup would be the better way to go. And this is another example of the difference between the robotic scopes and a pretty high-end imaging rig. The picture on the top was, I don't know the particular specs of this telescope, but it was taken from another club member where you can see that these are both of the Fireworks Galaxy, and you can see the details a lot greater in the top picture. And that's a combination of his scope had more aperture, had more focal length. His sensor might have been higher resolution, and he probably went for a lot longer integration time. He might have used filters, might have used a monochromatic camera, a lot of things, and he's much more skilled in post-processing. In the Vespera, stars are fatter, and you don't have quite as much detail. But if you compare the amount of effort it took to get each of these images, the Vespera was pretty effortless to get this. So in conclusions, these robotic telescopes are fun for the larger showcase targets. You can easily image right away with very little effort in both setup and the imaging process. And some of them give you a TIFF file for easy editing afterwards. And some of them have a Mosaic feature built in, which is really nice for the larger stuff. The bad is they don't work for smaller targets like planets and very small galaxies. They're not modular, so you can't reuse any of your existing equipment. And it is possible, as we just saw, that you can do better with high-end equipment if you want to take your imaging hobby to the next level. And so far, all of these robotic scopes are made by these new companies. So there's always the question of, will these companies last? So there's no answer to that yet. We hope they will, but we'll just have to wait and see. Okay, that's all.